Ignition sequence start. 6, 5, 4, 3, 2, 1, 0. All engine running. Liftoff. We have a liftoff. 32 minutes past the hour.
Hello, and welcome to the second episode of On Air, Actually Rocket Science. During the duration of this podcast, which is organized by the Student Council of Aerospace and Geodesy, we will be interviewing the professors of our departments and dig deeper into their fields of expertise. I am Greta, a third semester aerospace bachelor student, and this is Paula, a first semester student. And today we have the great honor of welcoming Professor Chiara Manfletti on our podcast. Thank you for joining us.
Thanks for having me here.
It's great that you found the time to come and join us today. I would just briefly introduce you to our audience. Well, Professor Manfletti leads the Space Propulsion and Mobility Chair at TUM. And she has worked in this field for many, many years, and she has gathered an astonishing amount of experience, and which is also why we as students are very grateful to have you. She has also worked in very important space agencies such as the DLR, as well as the European Space Agency.
Okay, how about we start with a quick game of this or that? We will ask you some questions and you can answer with what you prefer. First up, startup or government agency?
Oh, startup.
Liquid or solid hand soap?
Liquid.
Bees or birds?
Oh, that's evil. Bees.
Management or research?
Oh, innovation.
Open or closed engine cycles?
Closed.
Okay, great. So we would like to start off with your career. And so you have basically gotten a master in aeronautical engineering in London.
Correct.
And then a second master in space studies at the International Space University in Strasbourg.
That's correct.
And then you concluded your doctorate in Germany, and your focus was on liquid rocket engines.
Absolutely, yes.
Okay, so when I first saw your curriculum vitae, I was very impressed because you have done many, many things. And the first thing that I was wondering is, have you always imagined yourself following this path?
No, I didn't, actually. When I was a little child, my dreams were all over the place. I have to admit that even picking studies for university was very hard for me. I could imagine being everything from a marine biologist to a veterinary, to a lawyer, to a journalist. So it was very hard for me to pick, especially because I couldn't imagine what my days would be like. So I remember actually one day I went to my dad and I actually asked him, "Dad, what you do?" And he's like, "Well, you know what I do." I'm like, "No, what do you do the whole day?" So I really couldn't imagine what also my day-to-day life would look like. And that was also part of something important for me at the time.
And how did you then kind of get into this, like, how did you start following this path? Like, what was the moment you realized this is what I want to do?
Well, when I started thinking about it, I realized that becoming an engineer is something that I could have really liked. I remember, again, my dad sort of fixed stuff around the house, and I remember following him all over the place, wanting to see how he fixed stuff and wanting to fix things as well. So I thought hands-on engineer sounds good. And then it was just a question of picking the type of engineering. And at the time, I actually went to visit the Politecnico of Milano. And I wanted to see, what kind of engineering types there could be. And I thought, okay, aerospace engineering could be interesting. And then one day I was at home, I was still thinking about it. And I was actually watching TV with my parents, and a video came online about the Cassini-Huygens mission of ESA. And I saw the Huygens probe land on Titan. And I was just so charmed. I thought, okay, I'm going into space.
That's a very interesting story. And when you finished with university, how did you basically get started right afterwards?
I finished university in Imperial College, and at the time, as you said, I was doing aeronautical engineering, and I actually really wanted to do space, so I went to the International Space University. One of the reasons I went there was because I could have the chance of doing an internship in space, and specifically in propulsion. I realized early on that propulsion's like one of the enabling key technologies for us to do space. No propulsion, I thought, no, nothing, because we can't get into space. And so the internship possibility, and specifically at a company, SNECMA, that was integrating and still is integrating, but under a different name, the big engines for Ariane, was something I wanted to do. So that's how I started getting involved, and I did my first internship at the time. If I can just tell you a little bit more of my story. The Ariane 5 had actually a failure. I was actually hoping to start working at SNECMA, but the Ariane 5 had a failure, and there were two issues. One, which they would probably not like me sharing, but I'll share anyway. I had an Italian passport at the time, and just an Italian passport, and SNECMA being a French company, they were afraid of a bit competition from Italy, so they were afraid I was going to work there and take away secrets to Italy, something I couldn't really understand because I felt very international, very European, so, it was just beyond me. And the other thing, as I said, there was Ariane failure. So what happened then is that I started looking into doing PhDs, and that's when, through a guy who knows a PhD supervisor who knows a professor at university, that's how I came into contact with DLR, and that's how I then started doing my PhD at DLR.
That's impressive. That's
It
actually
really
very
is.
interesting. Yeah.
You spent nearly 14 years working at DLR, first focusing on space transportation and then on liquid rocket propulsion. During that time, you also started your research on laser ignition methods, on which you wrote a couple of papers, and which is a possible alternative to traditional electrical ignition systems. Can you explain to us in simple words what laser ignition is and how it works?
Yeah, it's pretty cool. So in general, when you want to have ignition, you have to have some energy source that you bring into a combustion chamber where there's fresh propellants to combust. And in classical methods in rocket engines and liquid rocket engines, what you do is you start a pilot. A flame is like if you turn on, what do you call it in English now? A lighter, thanks. It's like you having a lighter in your combustion chamber, right? So you have what's called a pilot torch flame, and these hot gases come from somewhere else. So it either comes from hot gases which are burned inside an igniter chamber, or they come from a solid charge, which is sort of combusts and also produces all hot gases. Now with laser ignition, what you do is you actually just focus a laser beam to such a small point that you actually have a plasma creation, and this becomes your energy source. So what you do is you directly focus the laser into the main combustion chamber, and then you don't have to have additional igniter system. And if you will, the key here is that, again, you're creating a very high energy and high temperature plasma that will act as a first flame kernel, which will then grow as you feed more fresh propellants to it. That's how fundamentally it works.
Well, thank you for explaining that. And since it's a completely different system, what effect would the implementation of laser ignition have on the performance of the thruster itself?
One of the things that we were doing when we were looking into laser ignition was looking at different propellants. Okay, so traditionally, if you look at propellants that are used for satellites, you have things like hydrazine, nitrogen tetroxide, monomethylhydrazine. These propellants are so-called hypergolic propellants, meaning that they ignite when they come into contact with one another. So they actually don't need to have an external ignition source. Now, these propellants are actually toxic, and they're cancerogenic. So there is a need to develop green propellants as well. Okay, so the idea of laser ignition was to actually have different propellants that weren't hypergolic but would need an ignition source, but not have something which is so heavy and needs an external igniter to function, but where you can actually ignite directly into the thruster. So if you will, again, how would a thruster change? Sorry, I had to make a detour. We would have different propellants to what we have today, and you wouldn't necessarily have an external igniter source, but you would still have the possibility of reigniting as many times as you have propellants that goes to the thruster. That was, if you will, one of the advantages of laser ignition when we were looking at it. The other thing is that when you have thrusters on a satellite, you use them for attitude control, pointing of your cameras, pointing your antenna. And what you generally have is multiple small thrusters. So we're not talking about the big launcher engines, but you can also use laser ignition for those. But we're talking about the small thrusters on a satellite. And here what you do is you pulse them at different times. And having laser ignition, you can also synchronously time them so that you can have exact ignition in the different thrust chambers at whatever time you need.
That's really interesting. So, reading through one of your papers on this topic, we saw that you worked with an experimental setup, and we were kind of wondering how that looked. Could you briefly describe how such an experiment works? Like, do you have a thruster? I mean, when I think of a thruster, I imagine like a big one. Do you have one just in a lab and set it up?
Well, okay, there's two parts, obviously, to this. There's the so-called test bench, and then obviously there's the hardware specimen, or the actual thruster or combustion chamber, or breadboard thruster, as they're sometimes called. So the actual test bench, these obviously vary depending on the types of propellants that you're testing. At the time, I was testing things like liquid oxygen and methane, or liquid oxygen and propane. So what you need to do is, unless you get delivered liquid oxygen in liquid form, you actually have to liquefy the oxygen. So what you have is generally a liquid nitrogen bath, because liquid nitrogen is liquid at 77 Kelvin and liquid oxygen is liquid at 90 Kelvin. So if you put a gaseous oxygen in a bottle in a liquid nitrogen bath, it would actually liquefy. So the test bench has a liquid nitrogen bath. You use that to cool your liquid oxygen, and then what you do is you have feed lines and valves that feed those propellants to a combustion chamber. Okay, so there's a whole huge amounts of infrastructure, lines, bottles, pressure reducers, pressure sensors, temperature sensors, even more valves, two-way valves, three-way valves, security valves. So it's lots of piping and equipment, and that's the actual test bench. And then what you have is a combustion chamber, and this is the part that really gets exciting, right? And what you do is when you test, of course, what you're trying to reproduce in a combustion chamber are the internal gas dynamics, the flow fields, combustion chamber temperatures, the profile of the combustion chamber itself, and you want to look inside. So what you end up doing is building a combustion chamber which maybe has the same profile as a flight hardware, but from the outside is a lot more sturdy and heavy, right? So, at the time I was testing with a combustion chamber that had a diameter, I think it was like something around 7 centimeters combustion chamber diameter, 3 to 4 centimeters throat, so it had a contoured shape to go to that sonic Mach 1 at the throat and then diverge again. And then I had little windows. Well, they weren't so small, but too small. You always want to see everything on both sides. And then one at the top for the laser, for actually focusing laser inside. And then at the bottom you have sort of all sorts of ports for temperature and pressure sensors. And yeah, that's more or less what it looks like. I don't know if I'm answering your question.
That was an answer.
I have a real picture in my head, but it's hard to sort of convey this.
No, I think you explained it really well.
Okay.
Actually, I just came up with one question. What are important parameters that you need to measure when doing tests like this, especially when talking about combustions and Yeah.
So at the time, obviously, I was doing so-called ignition tests. So for me, it was important to detect when exactly I was igniting the combustion chamber. So just imagine that you're feeding propellants into a box, and you wait and you wait and you wait. These propellants are going to mix more and more and more. And the longer you wait, the more propellants are going to be, the more well-mixed they're going to be, the harder it's going to explode, let's say, or combust when you actually have ignition. So one of the things that was very important for me was to actually measure the time between I actually had my laser pulse going into the combustion chamber, the creation of my plasma kernel, and the actual ignition, and the increase of the pressure curve in the combustion chamber. So for me, the time delay was important, the actual evolution of the pressure within the combustion chamber, any high frequency evolutions in the pressure were also very important. And because, as I said, I was only looking at the ignition time, I wasn't too worried about temperature. But obviously, if you then have longer combustion chamber times, you also want to check what your temperature is doing. And you look at many other things, I have to say, right? So when you're doing experiments, you also want to check how stable my combustion is. So you're not just looking at the pressure profiles and evolutions, but then if you have the possibility of looking at visually inside it, you'll check if your flame is actually anchored to the injector element. If it's not, it's, like when a candle flutters, it's because the flame isn't necessarily anchored at the bottom. So it starts flickering and everything. And you have the same thing in a combustion chamber. So yeah, there's many parameters, but those are just a few.
And do you think laser ignition is going to be something that's going to be implemented on a bigger scale, like used?
Well, at the time, we were actually planning on putting it on Ariane 6, and it was actually on the implementation course for it. I think there is, a potential for laser ignition. I think that there's also other laser, you see, I'm totally focused, other ignition methods that could be quite attractive. There's catalytic ignition, for example. Platinum is catalytic with hydrogen. There's other things that one could look into. But yeah, I think laser ignition has some potential. Ultimately, sorry if I just may add, it's a question of cost, right? Yeah. Today in space, we're really driven by cost, and then therefore that's what's actually going to ultimately drive if something like laser ignition is going to be used or not.
Is it a rather expensive technology, or is it affordable?
Of course, it's more expensive than just having a spark plug or 3 spark plugs. Clearly, it's more reusable. However, right? So there's advantages and disadvantages, and ultimately, it's also a question of how many you produce. Okay. At the time, I was working with a company that was also looking at using laser ignition for aircraft and also for trucks. So, if it's something that we produce just for space, then there's going to be just a couple of companies that are just going to produce, just a few numbers. We're not going to be anywhere near mass production, and the prices are going to be too high.
Okay, then I guess we can move on to the next topic. So during your time at DLR, you have also worked for a management position for many years. And we were wondering, how did this shift from, let's say, research-based to management-based work occur?
Well, it was kind of, it happened naturally in a sense, right? So it's never at least it wasn't for me, a dramatic change. So I started with managing or supervising a couple of PhD students, and then I had a bit more responsibility, and then I became responsible for a larger group. So the transition was, let's say, gentle, although it happened quite quickly. In terms of myself, I think I realized that when I was moving more away from actually doing research myself and managing it, I kind of realized that, my life was going to change. And I guess the only question I asked myself at the time is if it was going to be a change that I thought was going to be exciting for myself or not. If I were to have to abandon, all managerial responsibilities I have today, and someone would put me in a test bench and say, hey, do research, I probably would enjoy it for a little bit, but I wouldn't necessarily enjoy it for a very long time because, it's when you do management, you also get exposed to new things. Today, I would still have those questions of what's it good for, okay? And I like being able to contribute to making that what's it good for happen sooner rather than later. And I have a feeling that I can do that more in management than in other things. But I still like to be challenged on a technical level and have challenging technical discussions with my teams.
It's a very interesting point of view to seeing the whole situation. And let's say after the LR, you started working at the European Space Agency, where you became a senior advisor, which is a quite influential position in such a big agency, especially when we're talking about, space. And we know that engineering fields are mainly male-dominated. So we kind of get to the topic of how did you as a woman feel in this environment? Have you ever felt maybe, influenced in any way?
The only thing I ever felt was maybe young. I was generally younger than my peers. My peers were doing like semester, during the summer they were doing like semester work somewhere. And I thought, hey, why not? Let's do it as well, right? It's at the time, during my time, it wasn't very traditional for us in Italy to do it. But I thought, hey, I'll take this up and I'll try. So I called up an Italian company. I will not disclose which one. Otherwise, I'll make very bad publicity for them. And they said to me, but you're very young, because I had gone to an American school. I'd finished a year early. I'd studied in an English system, which meant that I was younger than most Italian students. And this weird lady on the phone was telling me I was young. Time, age has been more of a thing than woman or man, to be quite honest.
Why do you think that this happens?
Well, honestly, I'm starting to believe that our society hasn't learned to cope with neither young nor old. We sort of think the young can't do stuff and the old can't do stuff. And it's like, okay, and I don't actually agree with that. I think,
Not at all.
Yeah.
Do you think it is important to include everyone in science, or do you think that there's too much importance that is being given to gender in general?
Well, yeah, don't get me started on gender. I mean, I'm not too much of a fan of quotas and things like this, to be quite honest, right? I mean, I know you guys have some questions lined up for me at Neuraspace, and even in my time at Portugal Space, I hired whatever came across that was, I felt could be good to the team. And somehow I always managed to have teams that were 50-50. And I have no clue how I did it, but somehow it worked, right? And for me, it was never a question of quota. Now, of course, I understand that, we need targets. I understand that, it's also a way of showing that it's important. But I do believe that it's more of a diversity thing than a gender thing, to be quite honest. I mean, I see it. I just see it talking to the two of you, right? We're three females, but we're very diverse, and I think that's what's in magic. We're diverse in countries and ages and everything. So and that's great.
It would be great if everyone had this mindset, in my opinion.
Yeah, I mean, I don't know, how much. Again, it's fair to talk about this whole quota topic, but I cannot imagine that there's any woman out there that also likes to be told that she's a quota woman. So yeah, I find that's a very difficult topic.
Yeah. But I mean, it is going up. I think we're 30% girls now in studying aerospace here. So it's gone up quite a bit, I think. We were talking about achievements that you like, having a certain achievements, and you mentioned the Portuguese Space Agency, which, I mean, you work together with the Portuguese government to build up their agency and get them a place in the space industry. We just have one question. Do you think politics and the government in general should play a part in the space industry?
Well, first of all, let me state that they do, okay? And it's important that they did, and they have so far. I mean, space is something which is important from a sovereignty point of view, and I think we all see it, in certain conflicts that we have and certain considerations. Space is important because it contributes also to the socio-economic success of nations and societies. So I think that the government involvement is good because it pushes this forward. Now, I also believe that there's a limit to where governments and, agencies need to be involved, and where, the private sector needs to step up. Fundamentally, it's also a question of roles and responsibilities, right? So if it's like having a very simple comparison, 2 cooks in the kitchen, who's ultimately responsible, make sure that you have a good dish coming out, right? So if there's too many people involved and responsibilities aren't clear, then I think not as much is done. And I believe that we need a active, self-standing, responsible, vibrant private sector. And for that, I think there's certain places where, governments and policies just need to adopt a different role to what they had in the past.
Yeah. While we're on the topic of politics, we have to take a short break, and we'll cut to Marius explaining a bit of university politics.
The first level of university politics relates to the individual cohort, meaning all the students that started your study program in the same year as you. Most day-to-day issues that occur are on this level. In the bachelor's, you elect semester representatives each semester. They are your direct contact when you have an issue regarding the study program or a course. Your semester representatives will help you in finding a way to go forward. If the problem relates to the entire cohort, they will try to solve the issue or relay your concerns to the student council. In the masters, the cohorts are a less meaningful distinction, and more relevant groups are often given by who shares a course. In master's courses, you may have to speak to the teaching personnel yourself. If you cannot solve a problem directly by yourself, or if a problem relates to the study program at large, you need to contact the student council.
So in 2016, you started lecturing at TU Darmstadt. And then since 2021, you have been basically professor at TUM in the Space, Propulsion and Mobility?
22.
22?
Yes.
Okay, 2022. Sorry.
I'm 1 year old at TUM.
You're very young. And the question is, what made you switch from, DLR management position as a, to a rather academia-based work?
Well, first of all, of course, I'm not just professor at Technical University of Munich, right? So I don't see it as academia. I see it as actually, contributing to innovation. So it's true, it's academia, but for me, it's innovation. I think also the way, academia is and what universities are becoming is also, transforming. It's been changing a lot, right? So universities are seen as incubators of new ideas, of, incubating startups and bringing, new ideas out and relatively quickly as well. So I saw in the university a possibility of, doing this, contributing again to innovation, having contact with students, something that I was, doing, let's say, initially in my free time at the Technical University of Darmstadt, because that was something I was doing just on the side because, and I just felt that when I was studying, there were certain things that I had not been given. I left university thinking, hey, I will go and build a rocket propulsion engine and I will, contribute to the first European human-rated launcher and I will do so in just a couple of years. Whoa. And then, reality hit me. And I thought, I think it's important to give students back my experience so that you take your energy and you make the most of it. However, knowing what's out there and what's, how you have to invest your energies and most, and, this combination of innovation and, sharing experiences, what got me back, I think, to a place like academia.
Since your current research topic is, as we were talking about, propulsion systems in general, we really want to dive into the rocket. Into the rocket science now. But before we do, I would like to ask you a rather philosophical question, which is, why do you think humans have the urge to explore space in the first place?
Can I just say just because?
Yes, of course.
Just because. No, I think it's in our genes. So, and it's a fundamental curiosity that we have. I was born curious. I'll probably die curious. And I think that's what drives us, or many of us. Not everybody's curious, right? It's not the entire humanity. Not everybody's driven by the same thing, but I think many of us are. And I think it's just curiosity.
Okay, so now we move on to the actual rocket science, as we were saying. So when we talk about rockets, we differentiate between solid and liquid rockets. Could you give a brief insight in both types and maybe briefly say what are the pros and cons of each?
Okay, so there's many more types as well.
Oh, okay.
There's nuclear and there's hybrid, but it's true that there's liquid and solids, and those, if you will, are the main two big categories today of what's flying. So in liquid rocket propulsion, you basically have tanks filled with liquid propellants. These are fed to a combustion chamber and they're combusted in this combustion chamber. And depending on the application, if you have a main stage engine or an upper stage engine, then you will have different pressures in your combustion chamber. And then between the tanks and your combustion chamber, you're going to have, again, all sorts of different types of piping and valves. But you may or may not have pumps. The function of pumps is to increase that pressure. from the tanks, where you generally have just a couple of bar. If we're looking at a main stage engine, like in Ariane or in Falcon 9, just a couple of bar to 200 bar in a main combustion chamber. So you need pumps. So that's how if you will a liquid rocket engine works. Of course, there's a couple more components to that, and in solid propellant. Or in solid rocket motors, what you just have is a motor casing. And inside you have a solid grain. That solid grain has a certain profile, and the flame develops over at the surface area of the solid grain. And depending on the surface area and the contour, then the thrust that develops, the mass flow that's burnt, is a function of that surface area. And so you can design, whereas with a liquid rocket engine, it's depending on the mass flow. With a solid rocket motor, is a function of how that surface area is and how it devolves over time that will give you the thrust at the exit of your thrust of your engine.
So it's not really a matter of how much how much solid material you have inside, but it also very much depends on the profile.
Yeah, obviously the amount will tell you how long you burn, but how fast you burn and how much will depend on that contour.
Okay, that's very interesting. And what materials are typically used in these type of solid propellants?
Oh yeah, there's all sorts of things in there, right? So there's binders, there's elastomers, there's aluminium particles. So there's different. What you generally have is a oxidizer and a fuel that are combined together in a mixture, which combines two. Yeah.
Mm-hmm. Now, talking about oxidizer leads us to the next question, which is more about like the liquid rockets. I mean, this is maybe a very obvious answer, has a very obvious answer, but could air ever possibly replace the oxidizer inside of liquid rocket?
Well, I mean, there are concepts where they liquefy air. But when you liquefy air, you don't just get liquid air, you get, partial components of that. Now, there's obviously advantages and disadvantages to liquefying air. Parts, if you look at the composition of air, lots of air is nitrogen. Nitrogen is not exactly the best oxidizer. There's advantages because you don't have to carry that propellant with you. Okay, that you do when you have liquid oxygen. The disadvantage is that you wouldn't have such a good oxidizer as you have, But scramjets work. I mean, there's plenty of engine types that work with air. So
we mentioned in the very beginning open and closed cycles. Could you maybe briefly explain the differences?
Difference between the two. So the fundamental difference is that in an open cycle, there's going to be a part of what comes from the tanks and goes towards the engine that doesn't go through the main combustion chamber. Okay. And in a closed cycle, everything that comes from the tanks goes basically through the main combustion chamber. What this means is that if something goes not through the main combustion chamber, it means that fundamentally some components are decoupled from others. So the system is not closed, it's open. Now, just to give you examples, there's a so-called gas generator cycle and there's a staged combustion cycle. Both engine cycles have two combustion devices, the main combustion chamber, and in the gas generator cycle, you have a gas generator. In the staged combustion cycle, you have a preburner. In the gas generator cycle, it's called gas generator because it produces gases for the turbines that drive the pump, that increase the pressure to the main combustion chamber. But the gases that drive the turbines, therefore go through the turbine, are expanded across the turbine, are then ejected on the side. Okay, in a staged combustion cycle, you obviously have, again, hot gases produced in the preburner. The hot gases go to the turbines, expanded through the turbines, produce thereby the work that you need to drive, the power you need to drive the pumps. But those hot gases, once they're expanded across the turbines, they're re-injected into the main combustion chamber. And that's why it's kind of closed.
And when we talk about thrusters in general, let's say the main concept or like the main law that they use is, let's say, the Actuall equals reactio law, right? Where you have a big action and you exploit the big reaction to kind of push up your thruster. Now, the question is obviously to achieve enough thrust, you're gonna have to have a combustion inside of your boosters. And how do you have to design boosters in general such that explosions are avoided?
Well, I mean, there's let's say a trivial answer that I could give you, and that's if you burn your propellants as it comes into your combustion chamber, you're not going to have an explosion, right? Because obviously the propellant doesn't accumulate long enough to turn into an explosion, right? When you have an explosion, it's because all of the propellant is burning all of a sudden. So if you gradually burn that propellant, then you're sort of limiting that explosion, right? Now, if you look at, for example, the Vulcan engine, it has like 300 and a little bit kilograms per second of propellant that go through that combustion chamber. And those 3,000 something kilograms per second are combusted per second and come out the other side as hot gases. And that's what produces the thrust and avoids the explosion. When I was talking to you before about laser ignition, if you wait too long and those propellants mix and the whole combustion chamber is filled with, high density, very well mixed, then of course you're going to get a very hard, combustion. And that's going to be, peak pressures, and it's going to be more like an explosion. Yeah.
And how does rocket propulsion differ in the Earth's atmosphere compared to when it's in space? I mean, obviously you're going to have different components inside of your outside, like in the environment, but I mean, especially when talking about the efficiency and just the overall.
So what happens is, if you look at a rocket engine, it has a Laval nozzle, right? So it has a combustion chamber cylindrical part, and then it converges to the throat. You have Mach 1, then it diverges again, and you have an expansion ratio, which allows you to accelerate the hot gases to Mach 4 plus. Now, when you expand, you're expanding also to a lower pressure. Okay, so let's say you have 200 bar in your combustion chamber, and at the exit, let's say you're at sea level, you have 1 bar atmosphere. You're expanding to pressures that are maybe slightly lower than sea level, but you don't want to expand too much below that, because otherwise you have the atmospheric pressure acting on your hot gases, and they will compress and they will actually re-enter the nozzle, and that's going to cause flow separation, and then the hot gases are going to separate from the nozzle. That's going to create all sorts of problems that we want to avoid. And obviously, when you're in vacuum, you don't have this problem, okay? So what happens is that you're actually going to expand as much as you can with the nozzle that you have, but you won't be able to expand further using the nozzle. Okay, so your hot gases are going to be under-expanded because you won't be able to expand to zero pressure. You can't do that with a nozzle unless you have an infinitely long nozzle with an infinitely large expansion ratio. So that's basically, if you will, what changes. The performance increases because you have that under expansion, and your performance increases. But other than that, I'm trying to think if there's any other thing that changes as such. Of course, there's, in terms of the rocket itself, there's aerodynamic drag, which isn't a factor anymore. So you can dump, for example, the fairings, and you become lighter.
And in terms of, let's say, design requirements, is there anything that must be taken into account because of this performance difference?
Well, of course, you need to pick the right nozzle type and expansion ratio that it's fit to the trajectory part that you're flying, right? So if you have an engine which is going to start at sea level, you're not going to have a huge expansion ratio because that will cause side loads if you have that separation of the hot gases from the nozzle. And if you're higher up, then you can actually have a larger expansion ratio. So the design has to be tailored to the phase of the trajectory that the rocket engine is being used for that launcher that you've designed it for.
Well, okay, so when we hear propulsion systems, at least since we're studying aerospace, our first thought goes to rockets, but other aircrafts also make use of this system. What is the difference, you'd say, between rocket and jet propulsion, specifically when talking about working fluids?
Well, of course, when again, I was talking about liquid oxygen and liquid hydrogen, right? Liquid rocket engine actually has to take its propellants with it. And these are liquid. So, I mean, liquid oxygen is liquid at 90 Kelvin and 1 bar atmosphere. So we're storing, liquid oxygen at, let's say, 3 to 4 bar and 90 Kelvin. Okay, and liquid hydrogen is liquid at 20 Kelvin, and we're storing it at something again like 3 to 4 bar and 20 Kelvin. And with jet engines, you're not, you have the kerosene in your tanks, and the air is the air of the atmosphere. So that's fundamentally one difference. Of course, there's also kerosene engines that are used. There's other types of propellants as well. But if we think of the liquid cryogenic engines, the difference is ginormous.
Also, given the fact that rockets can reach supersonic speeds, could RAM or SCRAM jets be used as a replacement for chemical propulsion systems?
Well, only to get to a certain altitude, for sure, right? Because at some point there's no atmosphere anymore, so you can't. That's why there's things like rocket-based combined cycle engines that have been thought in the past. They don't fly. And rocket-based combined cycle is exactly the combination, if you will, of a SCRAM jet plus a rocket. And then you have a first part where you're flying through the atmosphere with first a RAM, then you go into SCRAM mode, and then when you don't have any atmosphere anymore, you go into rocket mode. Now, there's a whole debate whether SCRAM jets can actually be used to fly to the altitudes, and then these, let's say, rocket-based combined cycle can actually be used to fly to the altitudes that we want them to, because classically, if you look at rockets today, we have staged rockets, meaning that you have multiple stages, and once you've sort of emptied the tanks of a certain stage, you just throw them on the side because you're taking empty weight with you up and you don't need it anymore, and it just reduces your performance. Now with the scramjet concept, you can't just dump your scramjet on the side. Imagine how many billions of that worth, just say bye. You wouldn't do that, right? So a scramjet concept would be something that either flies back or is a single stage to orbit. So the entire concept of operations and the type of launcher becomes different. And then, but the answer is yes, but.
Okay, and since we're talking about scramjets already, every aircraft and spacecraft maneuver causes a change in the shockwave shape inside the scramjet engine. How do engineers keep it running? Because it must be so difficult to predict all the options that could happen.
Okay, so now this is my understanding of how a scramjet works. If you integrate it in a scramjet in a vehicle, okay, what you have is, and there's quite nice, studies that have been done in the past, because this is something that's been sort of researched a lot, especially in the 70s and 80s, Zenga concept, and then, whatnot. I mean, there's very many concepts. You have a vehicle which has, and now I'm holding the microphone, it's going to be hard for me to show you, but there's a vehicle at the tip of the nose. There's actually a shock wave that will leave that, and that shock wave goes towards the tip of the of the lower lip of a scramjet, and that is actually is basically the entrance cross-sectional area. If you integrate it over the surface or for the volume, it's going to be the entrance area of your to your scramjet, and that's going to dictate the volume of the air coming in, and that's going to dictate obviously the density. Obviously that's going to vary, but what you do is you actually design your scramjet in such a way that you have a part at the beginning where the shocks sort of transition from these oblique shocks to a normal shock, okay? And the important part is that you get to a normal shock where you then have pressures in there which are close to 1 bar, and temperatures which, if you're lucky, are close to like 700 Kelvin or so, because that's where then scramjets become auto-starting. You don't actually need an ignition system. So that's how it's done. You actually have to design your isolator, it's called the isolator, long enough so that you actually have the stabilization element in place, and you have that recovery of the pressure through all of these shock system to that more or less 1 bar. I mean, the people doing proper research on this, and that's not necessarily me, will then give you exact details as to, how far low you can go with the pressure, what kind of temperatures you need. And there's all sorts of, very nice investigations that they've made, and to see how the interaction is between the injected propellant and this flow, to see how the combustion then evolves. But that's what I remember of the whole subject.
Seems like a very complex
It is.
Yeah.
Fascinating, but complex.
Yeah. Okay, so getting back to rocket propulsion, how is the efficiency of a rocket's propulsion system measured? And talking about the future and things like that, what is the current front-runner technology in terms of rocket efficiency?
Okay, so now there's different ways of measuring an efficiency of a propulsion system or of a rocket engine. The specific impulse is something that we use. The specific impulse, if you will, is a measure of how much thrust you will get with a unit propellant. So the less propellant you need to produce a certain amount of thrust means that you are not just using propellants, which are in a sense more energetic, but also that the engine that you've built is doing that conversion better for you. Okay, so just to give you an example, liquid oxygen and liquid hydrogen are very good in terms of specific impulse. With an upper stage engine, where again we have that, we're just talking about pressure differential between atmospheric and what comes out of your engine itself, you can go up to specific impulses of 465 seconds, more or less. Okay, and that's, let's say, close to ideal what you can get with an engine. Liquid oxygen and hydrogen at sea level, you're not going to get as high specific impulse just because you can't expand as deep and all of these elements. Now, if you take other propellants, then that specific impulse, those 465, are going to go down based on, again, how the engine itself is designed, but also on the energy content of the propellants themselves, right? So, with certain systems, you can have just 320 seconds. So that's quite a loss, right? That's 140 seconds lost. So that's one way of doing it. But we also have efficiency for the different components, right? So we measure something like combustion chamber efficiency, and we have those efficiencies, or we have pump and turbine efficiencies. So it depends a bit. And then you using the different efficiencies within the combustion, within the different components, you can, if you will, create a global efficiency of the engine itself. And
Well, earlier we kind of mentioned the aspect of more environmentally friendly space travel. And obviously how the rocket itself and the propulsion system is chosen also has an effect on that. One step would be, for example, to use reusable rocket technology. What are the main challenges of such technology, and how can they be overcome?
So I think I've given you a bit of a feeling that, in rocket engines and liquid rocket engines, you have very high pressures, and we didn't really mention the temperatures, did we? But we have combustion chamber temperatures of like 3,200 Kelvin. So these are machines which are exposed to extremely high pressures and temperatures. Now imagine taking these through significant cycles. So one of the challenges, of course, is thermomechanical fatigue, right? And how do you care for that? The chambers, you're asking me about materials. The chambers are cooled. They have to be cooled because there's no material that's going to survive 3,200 Kelvin, right? So they're going to be cooled. And if you design that to withstand a number of cycles, then things can be reused. But to actually have rockets that are reusable, then of course you somehow have to bring them back to Earth. And then the question starts as to how you do that. Do you use your rocket engines? Do you fly them back? Do you have wings? Do you have parachutes? And that's where, in a sense, also the pure technical, optimal solution stops, and where other things start coming into play, just going off on a tangent, because you guys all know about, of course, SpaceX and Elon Musk and Falcon 9. So what he's doing is he's taking his engines with the Falcon 9, he's using it to take his rocket up, and then he still has propellant on board, and then he flips the stage around, and he lands again. So he's using propellant to work against the pull of gravity, and he lands, okay? Now, he could land with parachutes, for example, right? But then you'd have to have some soft landing of some sort. He could go with wings. If you look at Starship, he's actually using aerodynamic forces to decelerate the rocket quite a bit. So there's cleverness in the system of using aerodynamic drag to decelerate the rocket rather than just having the propulsive force in place. But there's been concept with wings, for example. If you have wings on board, you would never have a rocket which is just expandable. You would always want to reuse it because the effort of building wings, the investment needed for wings is far too big. So you would never just, throw that on the side. So the expandability that Falcon 9 has is an expandability or a reusability, which is like a kit reusability. So you can decide to be reusable. You don't actually have to. And you can do so if you have enough overcapacity, meaning you have more propellant that you actually need to service your customer that has to get into orbit. So as I was trying to give an example of how reusability is both a technical challenge, but there's other economic infrastructure considerations which come into play, which play a big impact onto how reusability is done.
Is there any other aspects of the system that can be changed to achieve a greener propulsion? Let's call it that.
Well, propellants for one thing, right? So, going to green propellants is certainly a good thing. Though I have to admit that if there's a high number of launches that have been made, the impact of, there's studies going on that wants to look into the impact of launches on the atmosphere. I mean, it gets very complicated. I'm not sure I understand us doing these studies, but there's, I think, also a limit to what makes sense. Because, I mean, if we want to be completely green, we should just stop all activities. So there's certainly how we manufacture elements, how much material we consume, how the propellants themselves they're used, the fact of not creating any waste when we are in orbit. That's also sustainability consideration, clean considerations. Rockets and satellites, when they sort of are injected into orbit, they sometimes lose bits and pieces. So those are also sort of greener considerations.
Okay, so we were talking about making the space industry more environmentally friendly, and that's why we would like to talk about Neuraspace, which is a startup that you have, worked for, still working for, and you are actually currently both the director and COO.
Yeah, correct. So I started as COO and got an upgrade.
Okay, that's and so the main focus of this startup is to use AI, artificial intelligence, to kind of either predict prevent satellites from colliding, as well as kind of tackling the issue of the space debris.
Yeah, so the point is that there's quite a number of objects up there. Quite a number are inanimate, and there are sort of big pieces and small pieces. But there's also a great number of satellites going up. And the point here is that if you need to know where the objects are so that you don't collide with them, or if there's two satellites in orbit which are active, that they also coordinate between themselves so that they don't collide. And then that's exactly where Neuraspace comes in, looks at potential conjunctions, so that potential times where things could collide, and then look at the risk associated with that. And if the risk is high enough, then what the software does that the company's developed is provides maneuvering advice, saying, okay, you have to move this way or that way according to certain criteria to avoid that potential collision from happening. Yeah.
What is the factor that drew you to this project?
Well, startup was one thing. Again, going back to innovation, right? There's, I think, various dimensions to this. I actually believe that when universities come together with industry, fundamentally, there's lots of magic that can take place because a university is a source of new ideas, and an industry is making that happen relatively in the short term. Going back to my impatience, right? So again, the marriage of university and a startup, which is like the most dynamic part of industry, is what drew me to also pursue a startup dimension to my life. And specifically Neuraspace, I think when I was at ESA and then I was in Portugal, the whole topic of space safety grew close to my heart. At the time when I was actually in Portugal, I also convinced the government that for a small country, I don't actually like to use the word small because it's sort of, it's not nice, but small in terms of financial contribution from a governmental point of view. If they wanted to sort of lead in a field, they would have to pick a field where there weren't big players acting. And space safety, meaning space debris, space weather, and near-Earth objects, was, if you will, the topic that I had identified as something. And then, that's how the story started. I mean, it's a much longer story. Nuno, the founder, he's a guy who's already sort of grew a company as well, and then grew it to be a unicorn. So at the time, I thought his business experience of growing a company together with my experience of being active in space, knowing the political environment, being active, I thought, okay, if magic doesn't happen there, I don't know what will. So that's a bit how it happened.
And what are, in your opinion, things that the space industry should improve or change in order to achieve an even better or like a more environmentally friendly operation?
Well, I think there's a number of things, right? So certainly tackling so-called space traffic management is one of them, for sure. Taking down objects that are no longer active is certainly another. Making sure that if a satellite becomes inactive, also it's automatically deorbited. These are certain things that can be done. Fundamentally, also we were talking about green propellants. I think that also wouldn't be a bad thing for sure. But fundamentally, I think that we need to think about, what I call a circular economy in space. Somehow in the past, and this is perfectly normal, space was seen as like one-off missions. We go to the moon, we've done that, been there, bought the t-shirt, well, if we could, but it's one-off missions. And I think now we're transitioning to a time where it's no longer one-off missions. Things build on one another. And for me, sustainability, it has to be both environmental, but you can't look for environmental sustainability if it's not economically implementable. Mm-hmm. And that's, for me, key. So going towards a circular economy in space also means looking into manufacturing in space, recycling in space, all of these fantastic things, which sound very, very science fiction-y, but I think are things that we need to consider. It makes no sense that we will forever bring resources from Earth into orbit. Somehow it doesn't make sense for long term.
And the use of AI has basically introduced a very big step in terms of modernization in the space industry. And do you think it might also have an impact on space travel?
Space travel?
Yes.
Oh, well.
Touristic space travel.
Touristic space travel.
Yeah.
AI is certainly a technology, and like many other technologies, it will contribute to advancing our adventure on Earth and in space. So yeah, for sure.
And do you actually believe in touristical space travel? Like, do you think it's a thing?
Well, if someone would give me a ticket to do that, I would. I was on a parabolic flight. I did the Vomit Comet, and I would certainly do a suborbital, trip if I could, if it wasn't that expensive. So yeah, I think I do believe in it.
Okay, and do you think that the AI would have also other important applications in the space industry?
Well, I believe in autonomy, meaning that if you look at the way we do space today, or how we operate our satellites, there is a very still strong human in the loop component, and I believe that we need to go towards more autonomous spacecraft. And this is where I think AI and machine learning can certainly contribute. In different ways, right? The AI and machine learning, they're very broad fields. If you just scratch a little bit the surface, it's like a huge field, right? You can get totally lost in it. But yeah, for sure.
And generally speaking, where do you see space going? Space industry overall. Hard question, I know, but
no. I'm just thinking of how to put this right. Sometimes, look, it's nice to be the space geek in the room, right? I don't know if you guys know this. It's a very old snippet where there's a guy coming into a party and he says he's a brain surgeon until a guy from NASA comes in and he says he's a rocket scientist, and he's like, well, it's not like it's rocket science, it's only brain surgery. So it's nice to be the geek in the room. Apologies for everybody who's listening who's in neuroscience. But anyhow, it's nice to be the geek in the room. But I think for space to go anywhere, space needs to stop, being the sector that's seen as the weird person in the room. It has to be like a sector, like every other sector. It has to be fully integrated with other solutions. When I was at the Portuguese Space Agency, I say this now still, but obviously in different roles. Space solutions need to be fully integrated with terrestrial solutions. And then it will just be commonplace. And when it's commonplace, it's, taking a train, taking a suborbital flight, taking a car. It's just it's going to be a flying car, of course, by that time. But yeah, it should become available to everybody. And so commonplacely cool, if there's such a word.
Yeah, I think maybe people see space industry in general still up in the stars, see it very far away. And I think making this kind of like step towards humanity and like showing people that it's really just not that geeky stuff that you were talking about. I think that's, yeah.
So we asked our listeners for some questions for you. So this is just things that they were curious about. First off, how far did you expect the space industry to progress when you were starting as a student? Like, could you imagine like what would happen in the future?
Well, I told you I was running around with like salami, pieces of salami on my eyes, thinking that I would design the next rocket launcher. So I think when I started out of university, I had a very ideal view of what everything could be. Ever since, things have obviously changed. I got a reality check. But I have to say I'm very happy with the way things are progressing, and I think the last couple of years have been, tremendous progress for the space sector. Certain things are still too slow, in my view. Again, permanently impatient person. And I think we can still go faster. Though I have to say that when I was back at the European Space Agency, one of the things I'm very happy I managed to do was set up the space safety program. So I feel adamant about this whole sustainability issue. And at the time, one of the things I kept on saying was we will see commercialization happen in this field so much quicker than anybody will ever imagine. And that's part also the story behind Neuraspace, and part of the story behind many other companies as well. And in that sense, so 20 years back, I didn't imagine. 5 years back, I did imagine. But hopefully my imagination will be lower than what it will become.
Then the next one is a bit of a more technical question. The student asked, what is your opinion on nuclear propulsion and its use for interplanetary travel?
So maybe how can I express my opinion? When I was back at DLR, I actually submitted a Wettbewerb der Vision, like an idea challenge, and my idea challenge was nuclear propulsion. So my opinion can only be positive. Now, obviously, nuclear propulsion is not good for everything because it has a so-called thrust-to-weight ratio. So the thrust that it provides compared to the weight that it weighs as a propulsion system is not tremendously good compared to other rocket engine systems. So it's not good for everything. But I think that it's good for certain things. And for interplanetary flight, it could certainly be a thing. Yeah.
So have you heard of a spin launch?
Yes.
And what is your opinion on it?
I'm not sure I have an opinion. Why do I say this? Fundamentally, I think that new ideas are cool. Now, to go from there to actually have an opinion as to the complete feasibility of it, I tend to wait to have these ideas or opinions because I like to see, I like to understand more of the concept before I give a judgment. Again, I'm more of a curious person more than a judging person, if there's such a category. So I think it's a pretty neat concept. One of the things I ask myself is how scalable it is. Okay, so the concept, I don't know if you ladies know, but the concept of spin launch is that they spin something up at a very high speed in a kind of a vacuum, and then they kind of let go of the sort of thing that they're trying to get into launch. It goes through a membrane, and it breaks through the membrane, and then it goes into the atmosphere. So what you're basically doing is you're providing a lot of delta V, which you normally get through expelling hot propellants from a nozzle in a different way. So it obviously works because they've shown it. The question is how scalable it is. How big you would have to spin, and how when does it stop being a realistic system? Because you have to maintain it also from a mechanical point of view, right? Because it's spinning, and every system which moves and rotates and has nuts and bolts into it also has some repairing and maintenance that has to be done. So again, I'm just wondering how scalable it is. And
so our last question is, rotation detonation engines are being developed right now. How is the stability maintained in such an engine?
So I'm not quite sure I understand the question, to be quite honest, meaning that, in a rotation detonation engine, what you have is that you have combustion waves rotating around. So it's inherently stable in a sense, right? Mm-hmm. So again, I'm trying to understand what the person who asked the question is asking. There's... I don't know, again, if the student that asked the question just saw, but there's a nice video of NASA having tested its first rocket detonation, rotating detonation engine just very recently, full scale. There's no real problem, right?
I think maybe also I'm just thinking, while let's say the thruster or like the launcher is or like this technique is used, if it has an impact on the actual like movement.
Oh, because it's like more pulse.
Exactly.
Exactly. Well, again, I advise the student to look at the video.
Okay.
Because it becomes you don't actually. It's not like a. Yeah, the student has to watch the video.
All right. And well, then I guess we are done with the questions.
Yes, just one last one. We're coming to the end of this episode. Do you have any advice you'd like to give students or anything you would like to say?
Well, yeah, I think one of the things that certainly always guided me, you were being so very nice about my adventure so far and everything I've accomplished. So one thing I can say is every time I came across an opportunity of doing something different, I never really asked myself if I could do it, but I always asked myself if I wanted to do it and if it was worth the effort. And I think those are that's the right way of approaching life, right? Don't be guided by your fears, know them, know your limits, but be guided by other things and certainly not your fears, because that's not a good way to go. And it won't make you strong leaders. If you look around the world, there's lots of leaders out there, and the worst leaders are the ones that are being led by fears. And that's not what we want. So that would be my one piece of advice.
Well, thank you.
Thank you very, very much for joining us on this episode today. It was a beautiful talk and beautiful chat. So I guess we say goodbye to you now.
It was a pleasure talking to you, really.
I had fun. It was my pleasure as well.
And to our listeners, we thank you for listening, and we ask you to stay buckled in for the next episode.